The bridge girder installation over Sugar Creek in northwestern Pennsylvania involved the use of a 150-ton link-built 238 HSL lattice boom crawler crane. Mecca's Construction employed this crane to lift and set 5 bulb-T pre-stressed concrete girders, each measuring 31.3 meters in length and weighing approximately 43,091 kilograms, to complete a 183 meters span on Route 322. Due to severe space limitations near the abutments and piers, a tandem lift configuration was not feasible. Instead, the team constructed a graded temporary bridge across Sugar Creek, which was securely connected to a custom-engineered crane platform. This elevated platform allowed the 238 HSL crawler crane to operate with sufficient reach and stability, positioned directly above the creek bed. Each girder was delivered and positioned for lifting using a multi-point rigging system. The crane boom was carefully configured with adequate counterweight and radius adjustments to accommodate the 103 feet load. Once rigged, the crane hoisted the girder approximately 21.3 meters above the water, swinging it into alignment over pre-prepared bearing seats on the concrete piers. On-site crews stationed on the pier caps used tag lines and signaling to guide the beam laterally and rotationally into final position. Upon contact, the girder was lowered slowly onto elastomeric bearing pads to ensure precise load transfer and alignment. This methodical and engineered approach enabled the successful placement of all 5 girders, despite the logistical challenges. The integration of the graded bridge and elevated platform was essential in facilitating single crane operations under constrained site conditions. The construction of the Osmangazi Bridge was a remarkable engineering feat, completed in 4 years on land, in the air, over water, and under the seabed. Before placing the tower foundations, the seabed was reinforced by driving 195 piles into the ground. Then, massive caissons were submerged to support the 247-meter-high towers. The suspension cables, totaling 3,054 meters, were installed using aerial spinning techniques. The deck sections were transported by barges and lifted into place with precision, even under strong winds and harsh marine conditions. Earthquake resistance was a key design factor, with simulations considering quakes occurring once every 150, 1,000, and 2,475 years. Both Japanese and Turkish engineers collaborated, developing unique methods to combat saltwater corrosion, extreme loads, and seismic threats. Every phase reflected innovation and determination, culminating in Turkey's longest suspension bridge across the Gulf of Izmit. The auger boring process begins with the careful preparation of the launch pit. Excavation is performed to the required depth and length, and steel sheet piling is installed around the perimeter to secure the pit walls. The bottom of the pit is then leveled, and a reinforced concrete base slab is poured to support the auger boring machine. Steel guide rails are accurately placed on the slab to ensure the machine stays aligned throughout the operation. Next, the American Auger 72 inches auger boring machine is delivered and lowered into the pit using a crane. Workers carefully position the machine on the rails and align it with the intended bore path. A thrust block is installed behind the machine and braced securely. This thrust block provides the reaction force needed to push the casing and augers forward during boring. Once the machine is in position, the hydraulic hoses are connected to the power pack, and operational checks are conducted. Lubrication and electrical systems are also tested. The crew prepares the initial sections of casing pipe and auger flights nearby. A laser-guided alignment system is set up at the rear of the machine to maintain precise grade and direction during boring. The first casing pipe is then lowered into the bore path and attached to the machine's drive chuck. Inside this casing, a section of auger with a helical flight is inserted, and the cutting head is attached at the front. With everything aligned, the operator activates the machine. The cutting head begins rotating, and the entire assembly is pushed forward into the soil by hydraulic rams. As the bore progresses, excavated soil is carried backward by the rotating auger flights inside the casing pipe. Spoil exits through the back of the machine and is collected in a trough or onto a conveyor system for disposal. After each casing pipe is fully advanced, the machine is stopped, and a new section of casing and auger is added. The casing sections are aligned, connected by welding or bolting, and the process repeats. To reduce friction between the casing and surrounding soil, a bentonite or polymer lubricant is pumped around the pipe exterior. This helps the pipe move forward more easily and reduces the risk of ground settlement. The crew continuously monitors laser alignment, thrust pressure, and spoil flow to ensure safe and efficient operation. This cycle of boring, spoil removal, and pipe/auger extension continues until the cutting head reaches the receiving pit. At this point, boring operations stop and the augers are withdrawn in reverse order. The casing pipe remains in place, forming a protective tunnel for utilities or product pipes. Finally, the boring machine is disassembled and lifted out of the pit. All support equipment and rails are removed, and the pit is cleared. Completion of a swimming pool using EPS blocks starts with the installation of the modular wall system, which provides both formwork and thermal insulation. After the concrete foundation slab is fully cured and been leveled, the first course of EPS blocks is laid along the perimeter of the pool, following precise layout markings. These blocks are manufactured with interlocking tongue and groove joints, which ensure proper alignment and structural stability during assembly. Each block has internal hollow cores that will later be filled with reinforced concrete. Vertical and horizontal reinforcement bars, typically U10 U12 mm steel rebar, are inserted into the preformed channels of the EPS blocks according to structural design specifications. The vertical rebars are anchored into the foundation slab and rise through the full height of the walls, while horizontal rebars are lapped and tied at each course to form a rigid reinforcement cage. Subsequent rows of EPS blocks are stacked in running bond pattern to avoid vertical joint alignment, which improves the mechanical integrity of the wall. Openings for technical elements such as skimmers, return jets, underwater lights, and suction fittings are cut out of the EPS blocks using hot wire tools or saws to minimize damage to adjacent areas. After the wall system is fully assembled and reinforcement is in place, the walls are filled with ready-mix concrete, usually C25/30th grade or higher. Using either a concrete pump or chute, the concrete is poured in lifts to prevent excessive pressure on the EPS walls and reduce the risk of deformation. Vibrators or manual rodding are used to ensure full compaction of the concrete within the EPS cores, eliminating voids and ensuring proper bonding with the reinforcement. Once the concrete has cured and structural strength is achieved, installation of the pool's plumbing and electrical systems commences. Pressure pipes for circulation, filtration, and drainage are routed through dedicated chases in the EPS blocks or embedded in the slab. Conduits for LED lighting and control systems are also installed and sealed to prevent water ingress. The cementitious waterproofing layer or flexible polymer-based membrane is applied to the internal surface of the pool shell. This layer serves as both a water barrier and a bonding base for final finishes. The internal pool surfaces, walls, and floor are then rendered or screeded with mortar to achieve a smooth and level substrate. The final interior finish is applied depending on the client's preference. Typical options include mosaic or ceramic tiles fixed with waterproof adhesive and grout, or a PVC liner heat welded into place for a seamless, watertight finish. The pool coping is installed along the top perimeter, often using precast concrete elements or natural stone with a bullnose profile to ensure safety and aesthetics. Finally, the filtration unit, skimmer, circulation pump, and chlorination system are installed in the designated technical room. The system is pressure tested and adjusted for correct flow rate. The pool is then filled with water and treated with disinfectants and pH regulators to achieve proper chemical balance. EPS block pool construction provides rapid installation, high thermal efficiency, reducing heat loss, and precision-engineered geometry. The monolithic concrete core combined with the insulating EPS envelope results in a durable and energy-efficient swimming pool structure suitable for residential and commercial applications. The pipeline construction process begins with aligning and securing individual pipes on timber cribs. Depending on the diameter, typically between 24 and 48 inches, either hand welding or automatic welding is used. Skilled pipeline journeymen and welders handle both types. Before welding, the steel pipes are preheated within a specific temperature range. Where terrain prevents straight-line laying, journeyman pipe layers use cold bending machines to shape pipes to match land contours. A stabber guides the side boom operator for precise alignment, and a clamper secures the joints for welding. Automatic welding starts with a bead weld, controlled remotely. This is followed by multiple fill and cap welds to ensure permanent integrity. Each weld is marked with a control number for inspection and accountability. Hand welding typically involves teams of 2 welders, often under supervision for quality assurance. The downhand welding method is used, and all welders must pass a supervised test before starting work. Tie-ins connect finished pipe sections to the overall infrastructure. Throughout, welders and pipe layers focus on precision and quality to minimize defects and ensure cost-effective construction. These processes, along with continuous innovation, have transformed pipeline building into an efficient, mobile manufacturing operation that sets the pace for the entire project. The barrier production process begins with land clearing to prepare a stable work area. Then, a lean concrete layer is spread to form the base foundation. Steel reinforcement is set precisely, followed by the installation of conduit pipes within the rebar structure. Concrete is then poured using a slip form machine, which continuously casts and shapes the barrier. During pouring, slope tests are conducted to ensure concrete consistency. The barrier surface is finished smoothly while still wet. Expansion joints are created at specified intervals to prevent cracking. Drainage holes are also formed in the barrier to manage water flow. A curing compound is applied to maintain moisture and ensure proper concrete strength. Finally, the completed barriers are inspected for quality, forming a continuous, reinforced concrete structure along the highway. The construction process begins with ready-mix concrete delivered from a batch plant. This concrete, which uses normal weight aggregates and no fibers, is not initially suitable for form-free vertical placement. To modify its properties, thickeners and accelerators are injected and intermixed directly in the pumping line using a low-cost inline mixer. This creates a zero-slump yet highly workable concrete that can be pumped and shaped without conventional formwork.
And intermix in line some thickeners and accelerators as needed to give it properties that allow it to stand up without forms. In this case, we're using plywood to define the inside of the drain box.
In the first test, the concrete is used to construct a below-grade drain box. While plywood is applied to define part of the structure, it is mainly to guide geometry, rather than provide form support. In another test, a vertical wall is formed in mid-air using 2x4 boards to define the wall's plane, and additional boards are used as screeds, similar to finishing a concrete slab, but vertically. Steel reinforcement is added during the pumping process. A mock-up wall section is then created with 4 inches of concrete and foam insulation on the exterior. The foam panels act as stay-in-place forms. Additional seismic boundary reinforcement is included where required. Despite using a 1970s Mako grout pump normally unsuitable for stiff mixes, the system performs efficiently. The result is a clean, solid wall structure. This method supports taller walls and conventional finishes, making it suitable for 3D concrete printing and retrofitting projects. The Vermeer T1255 trencher cuts rock using a rotating drum, then conveyors transfer debris away, forming a clean trench. The construction of the new Auger barrage involved multiple key phases. First, steel sheet piles were installed at the upstream cofferdam to retain soil and support excavation. This was done using a vibro hammer attached to an excavator. The vibro hammer, with a maximum centrifugal force of 1,625 kilonewtons and frequency of 1570 RPM, drove interlocking sheet piles to the design depth. Next, PRE formwork systems were used for concrete structures. These modular systems were quickly installed using jack supports, providing high-quality surface finishes with minimal manpower. Concrete pouring was carried out using the Rotex Superswinger conveyor system and a high-capacity concrete pump. The Superswinger's boom reach of 50 to 105 feet allowed precise concrete placement, while the pump delivered concrete at up to 163 cubic meters per hour with a 125 millimeter delivery line. Finally, large radial gates were installed on the main weir and under sluices. Each gate was mounted using hydraulic jacks and connected to a hydraulic hoisting system. The gates, ranging from 11.4 to 33.9 tons, were operated via local control panels. Each gate opened and closed at 1 foot per minute, allowing precise water flow management across the barrage's 71 radial gates. The existing chip-sealed pavement is cold in-place recycled using a Wirtgen County Route 3800 recycler and CSS1 emulsion. A Weiler windrow elevator transfers the recycled material to a Vogel Vision paver, which lays it evenly. Then, 1.25 inches of coarse aggregate is added to enhance the pavement structure. The surface is compacted to ensure proper bonding and density, completing the rehabilitation process with improved load-bearing capacity and durability. The concrete mortar is discharged into a metal bucket, kubel, from the mixing truck via a rear chute. The worker adjusts the chute to ensure accurate pouring. The worker adjusts the chute to ensure accurate pouring. Once full, the bucket is hoisted to the upper levels of the construction site. The mortar is then poured where needed. This method, using a crane with a bucket, is an alternative to concrete pumps and is suitable for transporting mortar to higher floors during building work. Throughout the process, workers coordinate closely to ensure safe and efficient handling of the concrete. The rebar tying process using the Smart Tie system begins with preparing the tying tool by attaching the Smart Tie device to an electric screwdriver. Workers then insert a metal clip into the device. Once ready, the worker positions the clip over the rebar intersection and activates the screwdriver. The device quickly wraps the clip around the rebars and twists it tightly, securing the joint in less than a second. This process is repeated at each rebar intersection. The clips come in various shapes, allowing for different tying configurations, such as 90-degree, 45-degree, or overlapping angles. The system reduces hand strain, improves consistency, and significantly increases tying speed. All components are made from aluminum and special steel, ensuring durability and lightweight. With minimal effort, workers can achieve strong, reliable ties while maintaining ergonomic posture and enhance safety throughout the process. The construction process of the 330 kilowatts Enercon E33 wind turbine in North Ayrshire begins with site preparation. Heavy machinery is used to excavate and level the ground, forming a circular pit for the foundation. A dense steel rebar cage is assembled in the pit to reinforce the structure. Once complete, concrete is poured to create a strong base capable of supporting the turbine. After curing for several days, the site is cleaned and prepared for delivery. Next, the turbine components arrive by transport trucks. These include the steel tower sections, the nacelle which houses the generator and control systems, the rotor hub, and the 3 long fiberglass blades. A large mobile crane is assembled on site to handle the lifting operations. Tower installation begins with the base section, which is lifted and anchored to the concrete foundation. 2 more sections are stacked vertically using precision alignment and bolted together securely. When the tower is fully erected, the nacelle is lifted and placed on top. Meanwhile, on the ground, technicians prepare the rotor assembly. The 3 blades are individually connected to the hub using specialized lifting frames and torque tools. Once fully assembled, the entire rotor is lifted in one piece and carefully attached to the front of the nacelle. Throughout the process, safety measures are strictly observed. Workers wear high-visibility gear and helmets, and each lift is guided by signalers to ensure smooth positioning. After mechanical installation, electrical systems are connected and internal checks are carried out. The completed turbine is then tested and commissioned.